The moon beckons, not as a haven, but as a challenge. For decades, humanity has envisioned returning to the moon and staying. However, the lunar surface is unforgiving. Fine, razor-sharp dust, regolith, can tear spacesuits and cause lung damage, as every Apollo astronaut experienced. The moon lacks Earth's protective magnetic field and atmosphere, exposing astronauts to 380 times more radiation than on the ISS, increasing cancer and cataract risks. Temperatures swing from 260 degrees 127 degrees during the day to 280 degrees 173 degrees at night, causing structural fatigue, and the lunar night lasts for weeks, requiring alternative energy sources. If you feel that same tension, that pull toward something we're not supposed to see, hit like, subscribe, and comment your thoughts. And if you want others to join us on this journey, share the video. X, Facebook, Reddit, anywhere you can. You're the reason stories like this reach beyond the algorithm. Thank you for being awake. Despite these hazards, NASA, SpaceX, and international coalitions plan permanent lunar cities and outposts. The European Space Agency envisions a moon village, while SpaceX aims to send its Starship spacecraft for long-term missions. NASA's Artemis program seeks to land the first woman and the next man on the moon by 2025, targeting the South Pole. China also plans crewed lunar missions in the 2030s. Before building lunar habitats, we must ask, what are we moving into? The moon's surface is scarred by craters, and its regolith contains trace amounts of water, vital for life support and fuel, but extracting it requires advanced technology. The moon's low gravity aids launches but causes muscle atrophy and bone loss in humans. What if the moon resists our presence? These questions will define the future of space exploration. The moon's allure persists, symbolizing human ambition and curiosity. Whether welcomed or not, we will return, driven by the spirit of exploration. In the silence of the lunar surface, astronauts will leave their footprints once more, embracing the harsh beauty of our celestial neighbor. Segment 1. First Contact. Imagine the first human footprint on the moon, a symbol of triumph, of curiosity satisfied. But what if that footprint stirred something far older and far more relentless than human ambition? Lunar dust. It has been grinding rocks for 4 billion years, long before life existed on Earth, and it will continue long after we're gone. Under an electron microscope, lunar dust particles resemble medieval weapons, sharp, jagged, and coated in a glassy shell formed by micrometeorite impacts. These impacts vaporize the lunar surface, and as the vapor cools, it condenses onto nearby particles, embedding tiny specks of metallic iron. Iron that makes the dust magnetic. Iron that may generate reactive oxygen species when it comes into contact with human tissue. The Apollo missions brought back 842 pounds of lunar material, including dust, and scientists have been studying its properties ever since. The glassy coating on the particles, formed from the rapid cooling of molten rock, gives them a unique texture that is unlike anything found on Earth. This texture is so abrasive that it can wear down even the toughest materials over time. For instance, Apollo astronauts reported that the dust wore through 3 layers of their boot material in just 3 days, a material designed to withstand the harsh lunar environment. Preliminary studies suggest that this nanophase iron could trigger oxidative stress in cells, leading to inflammation and long-term damage. The sharp edges of the particles can cause mechanical damage to lung tissue. Prolonged exposure could lead to pulmonary fibrosis, a progressive scarring of the lungs with no cure. Researchers have found that lunar dust can penetrate deep into the lungs, bypassing the body's natural defenses. In studies conducted on mice, exposure to lunar dust simulants caused significant lung inflammation and damage within just a few weeks. The effects were comparable to those of silicosis, a debilitating lung disease caused by inhaling silica dust. Further studies have shown that lunar dust can also impair the function of macrophages, the immune cells responsible for clearing debris and pathogens from the lungs. This impairment could leave astronauts more susceptible to infections and other respiratory issues. In addition, the dust's ability to generate reactive oxygen species can lead to cellular damage and DNA mutations, increasing the risk of cancer and other diseases. But the real danger comes from the moon's lack of a magnetic field. With nothing to deflect the solar wind, lunar dust becomes electrostatically charged. During the lunar day, ultraviolet radiation strips electrons from the particles. At night, the solar wind bombards them with more electrons. The result? Dust that behaves like iron filings near a magnet, clinging to everything it touches. This electrostatic charge makes the dust cling to spacesuits, equipment, and even the skin of astronauts. The Apollo astronauts reported that the dust was impossible to brush off, and it often tracked into the lunar module, contaminating the living space. The dust's electrostatic properties also cause it to levitate above the lunar surface, creating a phenomenon known as horizon glow during sunrise and sunset. This glow, visible in photographs taken by Apollo astronauts, is a stark reminder of the dust's omnipresence and the challenges it poses. The levitating dust can also create a haze that obscures visibility, making it difficult for astronauts to navigate and perform tasks on the lunar surface. Astronauts during the Apollo missions struggled with this dust. It gummed up the joints of their spacesuits, making it difficult to move their arms. It wore through 3 layers of Kevlar-like material on their boots in just 3 days. And the symptoms began. Watery eyes, scratchy throats, coughing, nasal congestion. The missions were short, and the symptoms resolved once the astronauts returned to Earth. But what happens during a 6-month mission or a permanent lunar base? The longest Apollo mission, Apollo 17, lasted just over 12 days on the lunar surface. Future missions, such as those planned under NASA's Artemis program, will involve stays of at least 30 days, with the ultimate goal of establishing a permanent human presence on the moon. Long-term exposure to lunar dust could lead to chronic health issues, including lung cancer, heart disease, and neurodegenerative disorders. The constant abrasion and inhalation of the dust could also accelerate the aging process of human tissues, further complicating the challenges of long-term space habitation. The dust's ability to infiltrate and contaminate living spaces could also lead to psychological stress, as astronauts would constantly be reminded of the dust's presence and the potential harm it could cause. NASA's Lunar Airborne Dust Toxicity Advisory Group released a report recommending a preliminary permissible exposure limit of 0.3 milligrams per cubic meter for a 6-month mission. That's similar to the exposure limit for crystalline quartz, a known carcinogen, but the report assumed astronauts would only be exposed 5 days per week. On the moon, there's no escaping the dust. Even inside habitats, dust particles can infiltrate air filtration systems, contaminate food and water supplies, and damage sensitive equipment. The fine particles can also interfere with electrical systems, causing short circuits and other malfunctions. The dust's ability to infiltrate and damage equipment is not limited to mechanical systems. It can also obscure solar panels, reducing their efficiency and compromising the power supply for lunar habitats. Additionally, the dust can interfere with communication systems, making it difficult for astronauts to maintain contact with mission control. The dust's presence on solar panels can reduce their efficiency by up to 50%, significantly impacting the power supply for lunar habitats. This could lead to power shortages and blackouts, jeopardizing the safety and success of missions. Electrostatic repulsion systems have been tested. Magnetic filters show promise. Advanced coatings might reduce adhesion, but none of these represent a complete solution. On Earth, if you have a dust problem, you sweep. On the moon, sweeping just makes it worse. The lack of gravity on the moon means that disturbed dust particles can remain suspended in the air for extended periods, increasing the risk of inhalation and contamination. Additionally, the abrasive nature of the dust can accelerate the wear and tear on mechanical systems, further complicating efforts to mitigate its effects. Researchers are exploring the use of plasma technology to neutralize the electrostatic charge of lunar dust, but this approach is still in its early stages. Other potential solutions include the development of advanced materials that are resistant to dust adhesion and the use of robotic systems to clean and maintain equipment. However, these technologies are still under development, and their effectiveness in real-world lunar conditions remains to be seen. One promising technology is the use of ultrasonic waves to dislodge dust particles from surfaces, but this too is still in the experimental phase. The question isn't whether we can overcome the dust, it's whether we can coexist with it. Because the moon has been grinding rocks for billions of years, and it won't stop just because we're there. The lunar surface is a dynamic environment constantly shaped by micrometeorite impacts and the relentless grinding of rock against rock. This ongoing process ensures that the dust will always be a part of the lunar landscape, challenging human explorers and settlers for generations to come. The dust's constant presence also poses a challenge for scientific research on the moon. It can contaminate samples, obscure observations, and interfere with experiments, making it difficult for scientists to study the lunar environment and its history. Despite these challenges, the scientific potential of the moon remains immense, and researchers are developing new methods and technologies to overcome the obstacles posed by lunar dust. One such technology is the use of robotic systems to collect and analyze samples, reducing the risk of contamination by human handling. The moon's dust is not just a scientific curiosity, it is a formidable obstacle to human exploration and settlement. As we plan for future missions, it is essential to understand the full extent of the risks posed by lunar dust and to develop effective strategies for managing and mitigating its effects. The success of long-term lunar habitation may depend on our ability to adapt to this ancient and unyielding adversary. The first footprints on the moon marked a historic achievement, but the true test of human ingenuity will be in learning to live alongside the dust that has shaped the lunar surface for eons. The challenges posed by lunar dust are not insurmountable, but they require a concerted effort from scientists, engineers, and policymakers to develop and implement effective solutions. By working together and leveraging the latest advancements in technology and research, we can overcome the obstacles posed by lunar dust and pave the way for a sustainable human presence on the moon. The development of advanced air filtration systems, for example, could significantly reduce the amount of dust that infiltrates living spaces and equipment, improving the safety and comfort of astronauts. Observation: lunar dust is not merely a nuisance, but a significant hazard to human health and equipment. Its unique properties, including sharp edges, electrostatic charge, and the presence of reactive nanophase iron, make it a formidable challenge for future missions. The dust's ability to levitate and remain suspended in the air for extended periods further complicates efforts to mitigate its effects. The constant bombardment of the lunar surface by micrometeorites ensures that the dust will always be a part of the lunar environment, requiring ongoing adaptation and innovation from human explorers and settlers. Interpretation: the symptoms experienced by Apollo astronauts provide a glimpse into the potential long-term effects of lunar dust exposure. Prolonged missions will require robust mitigation strategies to protect both human health and the integrity of equipment. The development of advanced technologies, such as plasma neutralization and robotic systems, could significantly improve our ability to manage the dust and mitigate its effects. However, these technologies are still in their early stages, and their effectiveness in real-world lunar conditions remains to be seen. The success of future missions will depend on our ability to adapt to the challenges posed by lunar dust and to develop innovative solutions that can withstand the harsh lunar environment. Speculation. As we look toward establishing a permanent lunar base, the question of how to coexist with lunar dust becomes increasingly urgent. Innovations in dust mitigation technology, habitat design, and medical protocols will be critical to ensuring the success and sustainability of human presence on the Moon. The lessons learned from these efforts may also have applications for future missions to Mars and other celestial bodies where dust poses similar challenges. The development of advanced materials, robotic systems, and plasma technology could revolutionize our approach to dust mitigation, making it possible to establish a permanent human presence on the Moon and beyond. By leveraging the latest advancements in technology and research, we can overcome the obstacles posed by lunar dust and pave the way for a sustainable human presence in space. The future of space exploration depends on our ability to adapt to the challenges posed by the environments we encounter, and lunar dust is just one of many hurdles we must overcome. Segment 2, Invisible Enemy Radiation, is the silent killer of the cosmos. On Earth, we are protected by our planet's magnetic field and thick atmosphere, but on the Moon, there is no shield. Astronauts on the lunar surface are exposed to a constant bombardment of radiation from the Sun and beyond. The Moon's lack of atmosphere means there is no natural barrier to deflect or absorb these high-energy particles, leaving astronauts vulnerable to both chronic and acute radiation exposure. Without protection, a 6-month mission to the Moon could expose astronauts to radiation levels equivalent to 24,000 chest X-rays, a staggering figure that underscores the severity of the threat. This relentless assault could lead to severe health consequences, including increased risks of cancer, cardiovascular disease, and cognitive decline. Apollo astronauts, for instance, experienced an average mission length of about 12 days. During this brief period, they received approximately 1.6 millisieverts of radiation per day, a dose rate nearly 3 times higher than that experienced on the International Space Station, ISS. During solar minimum, when the Sun's activity is at its lowest, astronauts can expect to receive about 380 millisieverts per year from galactic cosmic rays, 150 times the cosmic radiation dose on Earth. During solar maximum, the dose drops to about 110 millisieverts per year, still 45 times higher than on Earth, and that's just the background radiation. This persistent exposure increases the risk of long-term health issues such as cancer, cataracts, and cognitive decline. Studies have shown that prolonged exposure to even low-level radiation can accelerate aging at the cellular level, compounding the risks. For example, research on rodents exposed to chronic low-dose radiation has demonstrated accelerated aging in brain tissue, leading to impaired cognitive function and memory loss. The Apollo astronauts, who were exposed to relatively low doses of radiation during their short missions, have shown a higher incidence of cardiovascular disease, highlighting the long-term effects of even brief exposure to space radiation. The real concern is solar particle events. Occasionally, the Sun ejects massive bursts of high-energy protons during solar flares and coronal mass ejections. These events can release up to 10 billion tons of charged particles into space at speeds exceeding 1 million miles per hour. In August 1972, between the Apollo 16 and 17 missions, the Sun released a series of intense X-class flares. Had astronauts been on the lunar surface during that storm, they would have received a potentially lethal dose of radiation. The 1972 solar storm remains one of the most powerful on record, with energy outputs comparable to millions of hydrogen bombs. The storm was so intense that it caused widespread disruptions on Earth, including power outages and communication blackouts, offering a glimpse of its destructive potential in space. Satellites in orbit at the time experienced significant degradation, with some losing up to 50% of their solar panel efficiency due to radiation damage. These events are unpredictable. We can monitor the sun and get maybe a few hours of warning before a major flare reaches the moon. But that assumes someone is watching, that the communication systems are functioning, that the astronauts have somewhere to shelter. Even with advancements in solar observation technology, such as NASA's Solar Dynamics Observatory and the Parker Solar Probe, predicting the exact timing and intensity of solar flares remains an inexact science. The Parker Solar Probe, launched in 2018, has provided unprecedented data by flying closer to the sun than any spacecraft before it. But translating that data into reliable predictions is still a work in progress. For instance, the probe has captured images of solar wind streams and magnetic field reversals, known as switchbacks, which could help refine models of solar activity. However, these observations are complex and require advanced computational techniques to interpret accurately. NASA's current radiation limits prohibit increasing an astronaut's lifetime risk of dying from cancer by more than 3%. But historical solar particle events, including the 1972 storm and the October 1989 series, suggest that an unshielded astronaut on the lunar surface during a major event could easily exceed these limits. The October 1989 storm, for example, produced radiation levels that would have delivered a dose of over 400 millisieverts in just a few hours, equivalent to 10,000 chest X-rays. Such an event could render an astronaut's career over in a single blast. The storms of 1989 caused widespread disruptions on Earth, including the collapse of Canada's Hydro-Quebec power grid, which left 6 million people without electricity for 9 hours. On the Moon, the consequences would be far more dire. Without a functional power grid or backup systems, astronauts would face not only the immediate threat of radiation, but also the loss of life support systems, communication, and the ability to return to Earth. The solution, in theory, is shielding. Build habitats with thick walls. Use lunar regolith to bury modules under several meters of dirt. Keep water tanks between living spaces and the outside. During a solar storm, astronauts retreat to a heavily shielded safe room and wait it out. However, the practical challenges of implementing these solutions are daunting. Regolith shielding, while effective, requires excavating and transporting vast quantities of lunar soil. A single habitat module might need upwards of 3 meters of regolith coverage to provide adequate protection, equating to thousands of tons of material. To put this into perspective, the Apollo missions brought back a total of 842 pounds of lunar samples over 6 landing missions. Shielding a habitat would require moving tens of thousands of times that amount. For example, a habitat module measuring 10 meters by 10 meters would need approximately 3,000 tons of regolith to provide 3 meters of coverage, a logistical challenge that would require innovative engineering solutions. But none of this is easy. Regolith shielding works, but it requires moving enormous amounts of material. Robotic systems could handle the work, but they need to be operational before astronauts arrive and must function reliably in the harsh lunar environment. Water shielding is more compact, but water is heavy. Extracting it from lunar ice deposits is still experimental. And even if it works, you're depending on unproven systems to protect astronauts from a threat that could materialize with only hours of warning. The logistics of extracting water from lunar ice deposits, primarily found in permanently shadowed craters at the poles, are fraught with technical challenges, including extreme cold and limited sunlight, for power. For instance, the Lunar Reconnaissance Orbiter, LRO, has identified ice deposits at the Moon's poles, but these regions are in near-permanent darkness, with temperatures as low as 240 degrees, 400 degrees. Any extraction system would need to operate in these extreme conditions while maintaining efficiency and reliability. Recent measurements from China's Chang'e 4 lander suggest that astronauts on the lunar surface would be exposed to roughly 200 times the radiation levels experienced on Earth. The dosimeter aboard Chang'e 4 found that even with partial shielding similar to what a spacesuit would provide, the dose rate was about 1.4 millisieverts per day. That might not sound like much, but it adds up. A 6-month mission would result in about 250 millisieverts of exposure, approaching the annual limit for radiation workers on Earth. This constant exposure would significantly reduce the career longevity of astronauts, as lifetime radiation limits would be reached much faster. For perspective, the International Space Station, ISS, which orbits within Earth's protective magnetic field, exposes astronauts to about 0.5 millisieverts per day, highlighting the stark difference in radiation risk between low Earth orbit and the lunar surface. Even with shielding, astronauts on the Moon would accumulate radiation doses far exceeding those of their ISS counterparts. And that's just from background radiation. Add a solar particle event or two, and you could be looking at career-limiting doses. The longer-term concern is cancer. Ionizing radiation damages DNA. Most of the time, cells can repair that damage. Sometimes they can't, and mutations accumulate. Over years or decades, those mutations can lead to cancer. Studies of Apollo astronauts have shown an increased incidence of cardiovascular disease and mortality linked to their exposure to deep space radiation, underscoring the long-term health risks of lunar missions. Of the 24 astronauts who traveled beyond low Earth orbit during the Apollo program, 5 have died from cardiovascular issues, a rate higher than their counterparts who remained in Earth orbit. Similarly, studies on mice exposed to space-like radiation have shown increased rates of tumors and other health complications, further emphasizing the risks. We fear what we can see: craters, cliffs, the barren gray wasteland stretching to the horizon. But it's the invisible that kills first. The Moon's surface, though desolate and still, is a battleground of cosmic forces. High-energy particles from the Sun and distant stars bombard the lunar regolith, creating secondary radiation in the form of neutrons and gamma rays. These secondary particles penetrate deeper into materials, making shielding even more complex. Neutrons in particular are difficult to block, as they can pass through thick layers of shielding and interact with other materials, creating additional radiation. Astronauts would face a relentless invisible enemy, one that strikes without warning and leaves no visible scars. For instance, neutrons produced by cosmic rays can penetrate up to 2 meters of lunar regolith, meaning that even buried habitats would require additional layers of shielding to protect astronauts effectively. To mitigate these risks, NASA and other space agencies are exploring advanced shielding materials, such as hydrogen-rich polymers and nanocomposites, which could offer better protection at a lower weight. However, these materials are still in the experimental phase and have yet to be tested in a lunar environment. Additionally, researchers are developing more precise solar monitoring systems and predictive models to provide earlier warnings of solar particle events, potentially giving astronauts more time to seek shelter. One promising technology is the use of machine learning algorithms to analyze solar data in real time, improving the accuracy of flare predictions. For example, the European Space Agency's Solar Orbiter, launched in 2020, is equipped with advanced instruments to study the Sun's magnetic field and solar wind, providing valuable data for improving predictive models. Despite these efforts, the radiation challenge remains one of the most significant obstacles to long-term lunar habitation. The Moon's harsh environment demands innovative solutions and a willingness to accept risks that go beyond anything faced by astronauts in low Earth orbit. The success of future lunar missions will depend on our ability to shield astronauts from this unseen danger. Whether through advanced materials, robotic construction, or innovative habitat designs, the goal is clear: to create a safe haven on the Moon where humans can live, work, and explore without fear of the cosmic forces that seek to undermine their endeavors. Some proposals include inflatable habitats with built-in water tanks for shielding or modular structures that can be quickly assembled and buried under regolith. Other concepts involve using lava tubes, natural caves formed by ancient volcanic activity, as ready-made shelters, providing instant protection from radiation and micrometeoroid impacts. For example, Japan's Kaguya mission discovered a massive lava tube near the Moon's Marius Hills region, measuring approximately 50 kilometers long and 100 meters wide, which could potentially house an entire lunar base. The stakes are high, but the rewards, a deeper understanding of our place in the universe and the possibility of establishing a permanent human presence beyond Earth, are worth the risk. To fully grasp the stakes, consider this. A single solar flare could deliver enough radiation to cause acute radiation syndrome in an unprotected astronaut, leading to symptoms such as nausea, vomiting, and even death within days. The Carrington event of 1859, one of the most powerful solar storms ever recorded, released enough energy to disrupt telegraph systems worldwide, causing fires and electrical shocks. If such an event were to occur today, it could cripple modern technology, causing trillions of dollars in damage and leaving millions without power. On the Moon, astronauts would have no infrastructure to fall back on, making the threat of a Carrington-level event even more dire. For perspective, a Carrington-level storm would produce radiation levels on the lunar surface equivalent to receiving 10,000 chest X-rays in just a few hours, enough to cause severe radiation sickness or even death. Despite the challenges, the allure of the Moon remains irresistible. It is a stepping stone to Mars, a scientific treasure trove, and a symbol of humanity's ambition to explore the cosmos. But to realize this vision, we must first conquer the invisible enemy that lurks in the vacuum of space. Radiation is not just a technical hurdle. It is a test of our ingenuity, resilience, and determination to push the boundaries of human exploration. Every mission to the lunar surface will be a calculated gamble, balancing the promise of discovery against the ever-present threat of the cosmos's invisible killer. The Moon may be a harsh mistress, but it is one worth courting, for the lessons we learn there will shape the future of our species in the stars. As we look to the Moon and beyond, the challenge of radiation serves as a reminder of the unseen dangers that await us in the cosmos, and the unwavering spirit of exploration that compels us to confront them. Segment 3. The Furnace and the Freezer. The lunar day lasts about 29.5 Earth days. For roughly 2 weeks, the sun beats down on the surface, heating it to a scorching 127 degrees Celsius, hot enough to boil water. The lunar surface, lacking an atmosphere to diffuse heat, absorbs the relentless solar radiation until it becomes a furnace. The soil, composed of fine regolith, can reach even higher temperatures, up to 200 degrees Celsius in direct sunlight. Then, when the sun sets, temperatures plummet to 173 degrees Celsius over the course of the next 2 weeks. That's a swing of 300 degrees Celsius, a thermal roller coaster unlike anything experienced on Earth. The transition is so abrupt that it defies human intuition. Imagine standing on the Moon's surface as the Terminator line, the boundary between day and night, sweeps across the landscape. In a single step, you could move from temperatures hot enough to melt lead to cold enough to freeze oxygen solid. The stark contrast is not just numerical, but visceral. The glowing, relentless brightness of the lunar day gives way to a darkness so complete that it feels like stepping into an abyss. For context, the coldest temperature ever recorded on Earth was 89 degrees Celsius at Vostok Station in Antarctica. The hottest was 56 degrees Celsius in Death Valley. The Moon's daily temperature swing exceeds the entire range of temperatures naturally occurring anywhere on Earth's surface. Imagine the stark contrast. Death Valley's scorched landscape at its peak heat is a full 70 degrees Celsius cooler than the lunar day, while Vostok Station's frozen expanse is a staggering 84 degrees Celsius warmer than the lunar night. To put this into perspective, the difference between the hottest and coldest spots on Earth is a mere 145 degrees Celsius. The Moon's temperature swing is more than double that, occurring not over the span of a year or across different geographic locations, but every single lunar day in the same spot. This is not a gradual change, but a violent oscillation, as if the Moon itself is breathing fire one moment and exhaling ice the next. Materials don't handle this well. Metals expand when heated and contract when cooled. Do this repeatedly over hundreds or thousands of cycles, and eventually they develop stress fractures. Seals lose their integrity. Joints stiffen or fail. Electronics designed to operate within a certain temperature range suddenly find themselves outside it. The Apollo missions provided a stark example of this. Astronauts' cameras jammed in the extreme cold, and their spacesuits became brittle and inflexible when exposed to direct sunlight for extended periods. During Apollo 11, Neil Armstrong and Buzz Aldrin's boots began to delaminate as the extreme heat of the lunar day caused the glue holding the soles to fail. This wasn't just an inconvenience. It was a life-threatening malfunction in an environment where a single tear in a spacesuit could mean instant death. During experiments simulating lunar temperature cycles under vacuum conditions, researchers found that rocks subjected to these swings developed cracks over time. Different rock types fracture differently under these conditions, meaning dust behavior varies by region. For example, basaltic rocks, common in lunar mare regions, shatter into finer particles compared to anorthositic rocks found in the highlands, which tend to break into larger, more angular fragments. This variation in dust composition affects everything from rover mobility to the longevity of surface equipment. In some regions, the regolith becomes so fine that it behaves almost like a liquid, clinging to surfaces and contaminating mechanical systems. In others, the sharp angular fragments act like microscopic knives, cutting through seals and abrading materials over time. NASA and its partners are developing thermal management systems that can handle these extremes, radiators that efficiently dump heat during the scorching day, insulation that retains warmth during the freezing night, heaters that keep critical systems operational when external temperatures drop low enough to freeze carbon dioxide, which solidifies at 78.5 degrees Celsius. These systems are not just theoretical. They are being rigorously tested in lunar-like conditions here on Earth. For instance, NASA's Glenn Research Center uses vacuum chambers and thermal cycling to simulate the harsh lunar environment, ensuring that materials and components can withstand the extremes. One experiment involved subjecting a prototype lunar rover to over 500 temperature cycles, simulating more than 8 years of operation on the Moon. The rover's systems degraded significantly, highlighting the need for even more robust engineering solutions. But these are active systems requiring power and maintenance. They represent additional points of failure in an environment where failure isn't just inconvenient, it's lethal. For example, during the Apollo 13 mission, a faulty oxygen tank led to a catastrophic failure that nearly doomed the crew. On the Moon, such failures could be even more devastating, as rescue missions are not feasible. Every component must be engineered to operate flawlessly under conditions that push the limits of human and technological endurance. To address this, engineers are exploring redundancy systems and self-repairing materials. For instance, shape memory alloys could automatically restore their original shape after deformation, while self-healing polymers could repair microfractures in seals and joints. Every sunrise on the Moon is a furnace, every sunset a freezer. The surface is trying to kill you every 12 hours. The transition between day and night is not gradual but abrupt, with the terminator line, the dividing line between light and dark, creating a stark boundary where temperatures can vary by hundreds of degrees within a single step. This harsh reality underscores the need for innovative solutions, such as the development of phase change materials that absorb heat during the day and release it at night, or the use of lunar regolith as a natural insulator to shield habitats from the thermal extremes. One concept involves building habitats partially underground, where the regolith provides a natural buffer against temperature swings. Another idea is to use inflatable structures that can expand and contract slightly to accommodate thermal stresses, reducing the risk of structural failure. The challenge of surviving the lunar temperature swing is not just a technical one, but also a psychological one for future astronauts. The isolation and constant threat of the environment could take a toll on mental health. Psychologists are already studying ways to mitigate these effects, including the design of habitats that provide a sense of security and connection to Earth. For example, the use of virtual reality could allow astronauts to visit familiar places on Earth, providing a psychological respite from the lunar extremes. Lighting systems that mimic Earth's day-night cycle could help regulate circadian rhythms, reducing the risk of sleep disorders and depression. Additionally, the development of AI-driven companions could provide emotional support and companionship in an environment where human interaction is limited. As we look toward establishing a permanent human presence on the Moon, the furnace and the freezer will be constant adversaries. But with each technological advancement, each lesson learned from experiments and simulations, we inch closer to taming this inhospitable world. The Moon's surface may be trying to kill us, but human ingenuity is proving to be a formidable opponent. The Apollo program demonstrated that humans could survive on the Moon for short periods, but the Artemis program aims to establish a long-term presence. To achieve this, NASA is investing in technologies like in situ resource utilization, ISRU, which involves extracting water from lunar soil to produce fuel, oxygen, and even drinking water. This would not only reduce the need for costly resupply missions, but also provide a sustainable source of essential resources in an environment where every gram of payload counts. The lunar surface is a battleground of extremes, but it is also a canvas for human ambition. Every challenge, from the furnace to the freezer, from the abrasive regolith to the psychological strain, is an opportunity to innovate. By pushing the boundaries of technology and human endurance, we are not just preparing to return to the Moon, we are laying the groundwork for future missions to Mars and beyond. The furnace and the freezer may be relentless, but so is the human spirit. And as we continue to explore, adapt, and persevere, the Moon will become not just a destination, but a stepping stone to the stars. Segment 4. The Long Night. For 2 weeks, the sun disappears. Not gradually, the way it does on Earth, where twilight lingers and the atmosphere scatters light across the sky. On the Moon, when the sun sets, darkness falls like a curtain. No atmosphere means no scattered light. Stars and Earth provide some illumination, but not nearly enough to see by. For 14 days, the surface is plunged into a cold, absolute darkness. The temperature, which can reach a scorching 123 degrees Celsius, 253 degrees Fahrenheit during the day, plummets to a bone-chilling 173 degrees Celsius, 280 degrees Fahrenheit at night. This drastic swing, a staggering 300 degrees Celsius, 540 degrees Fahrenheit difference, poses monumental challenges for any technology or material exposed to the lunar surface. The lunar night is not merely an abstract concept, it is a tangible force that shapes every aspect of lunar exploration. For the Apollo astronauts, who spent only brief periods on the surface, the lunar night was a fleeting experience, a backdrop to their missions. But for future lunar inhabitants, it will be an ever-present reality, dictating the design of habitats, the operation of equipment, and the rhythms of daily life. This presents an immediate problem. Solar power doesn't work. Most spacecraft rely on solar panels to generate electricity. On the Moon, those panels are useless for half of each month. During the Apollo missions, this wasn't a concern. The astronauts were only there for a few days at a time, and their lunar module ran on batteries and fuel cells. The Apollo 11 mission, for instance, spent a mere 21 hours and 36 minutes on the lunar surface. Their equipment was designed for short-term use, not for enduring the brutal conditions of a lunar night. The Apollo 17 mission, the longest of the program, lasted just over 3 days, with astronauts Eugene Cernan and Harrison Schmitt spending about 22 hours outside the lunar module on moonwalks. Even during these brief missions, the lunar night was a looming presence, a reminder of the harsh reality that future explorers would face. The Apollo missions were a triumph of human ingenuity, but they were also a product of their time, driven by the political and technological imperatives of the Cold War. The Apollo program cost approximately $25.4 billion, around $152 billion in today's dollars, a staggering investment that reflected the urgency of the space race. The lunar module, a marvel of engineering, was designed to operate for only 45 hours on the surface, a testament to the limitations of the technology available at the time. The astronauts' spacesuits, though bulky and cumbersome, provided essential protection against the harsh lunar environment, but they were not designed for long-term use. The Apollo missions laid the groundwork for future exploration, but they were limited by the constraints of their era. But for a permanent base, or even a multi-month mission, you need a power source that functions during the lunar night. Nuclear fission reactors can provide steady power regardless of whether the sun is shining, but they're heavy, expensive, and politically complicated. NASA has been developing a small fission reactor called kilopower, designed to produce up to 10 kilowatts of electricity for lunar or Martian applications. It works in principle, but it's not flight-ready. And even when it is, 10 kilowatts isn't a lot for a full-scale lunar base. To put it into perspective, a typical household on Earth consumes about 1.2 kilowatts of power on average. A lunar base with its life support systems, communication arrays, and scientific equipment would require significantly more. The International Space Station, which houses a crew of 6 to 7 astronauts, requires about 75 to 90 kilowatts of power, highlighting the scale of the challenge for a lunar base. The Kilopower project, a collaboration between NASA and the Department of Energy, has demonstrated promising results in ground tests. The reactor uses a solid cast uranium-molybdenum alloy core, which is highly durable and capable of withstanding the rigors of space travel. The reactor's Stirling engines convert heat into electricity with an efficiency of around 30%, a significant improvement over traditional space-based power systems. However, the reactor's weight, about 1,500 kilograms, 300 pounds, presents a significant challenge for launch and deployment. Additionally, the political and regulatory hurdles associated with launching nuclear material into space are substantial, requiring international cooperation and stringent safety protocols. Batteries are the obvious alternative. Charge them during the day, drain them at night. The problem is energy density. Current lithium-ion batteries would need to be enormous to store 2 weeks' worth of power for even a modestly sized habitat, and batteries don't perform well at low temperatures. Below about 40 degrees Celsius, most batteries lose significant capacity or stop working altogether. Even advanced battery technologies like lithium-sulfur or solid-state batteries, which promise higher energy densities, struggle with the extreme cold. Researchers are experimenting with heaters and insulation to keep batteries warm, but these solutions add weight and complexity to an already challenging problem. For example, the Mars rover Curiosity relies on a radioisotope thermoelectric generator, RTG, to produce heat and electricity. But this technology is not without its own challenges, including the handling of radioactive materials. Lithium-sulfur batteries, for instance, offer theoretical energy densities of up to 2,500 watt-hours per kilogram, significantly higher than the 250 watt-hours per kilogram of traditional lithium-ion batteries. However, their performance degrades rapidly at low temperatures, and they suffer from issues like dendrite formation, which can short-circuit the battery. Solid-state batteries, which use a solid electrolyte instead of a liquid one, promise improved safety and energy density, but they are still in the experimental stages and face similar temperature-related challenges. Researchers at NASA's Glenn Research Center are exploring the use of advanced insulation materials, such as aerogels, to keep batteries warm during the lunar night. These materials, which are 99.8% air, offer exceptional insulation properties but are fragile and difficult to manufacture. Researchers are exploring advanced battery chemistries that might fare better in extreme cold, but these are still experimental. Hydrogen fuel cells are another option. Produce hydrogen and oxygen from water ice during the day, recombine them at night to generate electricity and heat. But this requires a working water extraction system, which again is unproven technology. The lunar regolith is believed to contain water ice, particularly in permanently shadowed craters near the poles. However, extracting this water and converting it into usable hydrogen and oxygen is a complex process that involves heating the regolith to temperatures as high as 1,000 degrees Celsius, 1,832 degrees Fahrenheit. This not only requires significant energy, but also risks releasing volatile compounds that could contaminate the extraction equipment. NASA's Lunar Crater Observation and Sensing Satellite (LCROSS) mission in 2009 confirmed the presence of water ice in the lunar regolith by deliberately impacting the Moon's south pole and analyzing the resulting plume. The LCROSS mission revealed that the lunar regolith contains about 5.6% water by weight, a significant finding that has sparked renewed interest in lunar resource utilization. However, extracting this water is no simple task. The European Space Agency's ESA prospect drill, designed to extract water from lunar soil, is one of several technologies being developed to address this challenge. The drill, which can penetrate up to 2 meters into the regolith, uses a heated tip to vaporize water ice, which is then collected and condensed for use. Another approach involves the use of microwave ovens to heat the regolith, releasing water vapor that can be captured and condensed. These technologies are still in the experimental stages, and their effectiveness in the harsh lunar environment remains to be seen. Electronics not actively heated will cool to the ambient temperature, somewhere around 150 to 170 degrees Celsius, depending on location. Many electronic components aren't rated for those temperatures. Transistors behave unpredictably, lubricants freeze solid, seals become brittle. Even materials like silicon, commonly used in electronics, can become brittle and crack under such extreme conditions. This poses a significant risk for any equipment left exposed during the lunar night. For example, the Lunar Reconnaissance Orbiter, which has been mapping the Moon since 2009, relies on heaters and thermal blankets to protect its sensitive instruments from the cold. The orbiter's Diviner Lunar Radiometer experiment has mapped the lunar surface temperatures in detail, providing valuable data for future mission planning. The Lunar Reconnaissance Orbiter's LRO thermal management system is a marvel of engineering, designed to maintain the spacecraft's temperature within a narrow range despite the extreme conditions of the lunar environment. The spacecraft's thermal blankets, made of layers of aluminized mylar and dacron, reflect heat away from the spacecraft during the day and insulate it at night. Heaters strategically placed throughout the spacecraft provide additional warmth during the lunar night, ensuring that sensitive instruments remain within their operating temperature ranges. The Diviner Lunar Radiometer experiment, one of 7 instruments on board the LRO, has provided detailed maps of the lunar surface temperatures, revealing the extreme temperature swings that characterize the lunar environment. Japan's Selene lander managed to survive 3 lunar nights by shutting down into a hibernation state and hoping its batteries stayed warm enough to restart once the sun came up. That's impressive from an engineering standpoint, but it's hardly a long-term solution. You can't run a lunar base by shutting everything down every 2 weeks. The Chinese Chang'e 4 lander, which has been operating on the far side of the moon since 2019, also employs a hibernation strategy during the lunar night. However, this approach limits the lander's ability to collect data or communicate with Earth during these periods, highlighting the need for more robust power solutions. The Chang'e 4 mission has made significant discoveries, including the detection of water-bearing minerals on the lunar surface, but its ability to operate continuously is constrained by the challenges of the lunar night. The Chang'e 4 lander, part of China's ambitious lunar exploration program, has made significant strides in understanding the lunar environment. The lander's Yutu-2 rover, equipped with a ground-penetrating radar, has provided valuable insights into the lunar subsurface, revealing layers of regolith and buried craters. The lander's scientific payload includes a low-frequency spectrometer, which has detected the presence of water-bearing minerals, and a neutron dosimeter, which measures the lunar radiation environment. Despite these achievements, the lander's hibernation strategy during the lunar night limits its ability to operate continuously, highlighting the need for more robust power solutions. The Chang'e 5 mission, launched in 2020, successfully collected lunar samples and returned them to Earth, marking a significant milestone in lunar exploration. NASA has identified surviving the lunar night as one of the top technical challenges for sustained presence on the Moon. Not just keeping systems alive, but maintaining operational capability. The difference between hunkering down for 2 weeks and continuing normal activities is the difference between visiting the Moon and living there. The Apollo missions were essentially camping trips, short, intense, and focused on exploration rather than habitation. A permanent lunar base, on the other hand, would require continuous operation of life support systems, scientific instruments, and communication networks. The Apollo missions laid the groundwork for future exploration, but they were limited by the technology of their time. Today's lunar ambitions require a new level of technological sophistication and reliability. The Apollo missions were a triumph of human ingenuity, but they were also a reflection of the technological and political landscape of the time. The Apollo program was driven by the Cold War rivalry between the United States and the Soviet Union, with each nation seeking to demonstrate its technological superiority. The lunar module, a marvel of engineering, was designed to operate for only 45 hours on the surface, a testament to the limitations of the technology available at the time. The astronauts' spacesuits, though bulky and cumbersome, provided essential protection against the harsh lunar environment, but they were not designed for long-term use. The Apollo missions laid the groundwork for future exploration, but they were limited by the constraints of their era. And here's the thing about the lunar night. It's not just dark and cold. It's isolating in a way that's difficult to convey. When the sun sets, you're not just losing light and heat. You're losing contact with Earth, at least partially, because solar panels on communication relays stop working. You're losing the ability to recharge, to move around safely, to conduct any surface operations that require visibility. The Apollo 17 astronauts, the last humans to walk on the Moon, described the lunar night as an eerie, otherworldly experience. They saw the Earth as a distant, shrunken blue marble, a stark reminder of their isolation. The mission's commander, Eugene Cernan, remarked on the profound silence and stillness of the lunar night, a stark contrast to the bustling activity of Earth. The Apollo 17 mission, the final voyage of the Apollo program, marked a significant milestone in human space exploration. The astronauts, Eugene Cernan, Harrison Schmitt, and Ronald Evans, spent over 12 days in lunar orbit, with Cernan and Schmitt spending 3 days on the surface. Their lunar module, Challenger, touched down in the Taurus-Littrow Valley, a region rich in geological features. The astronauts conducted 3 moonwalks, collecting rock and soil samples, deploying scientific instruments, and exploring the lunar landscape in their lunar roving vehicle. The mission's scientific payload included a lunar surface gravimeter, which measured the moon's gravitational field, and a surface electrical properties experiment, which studied the electrical properties of the lunar regolith. The Apollo 17 astronauts also left behind a plaque commemorating their visit, a symbol of human achievement and a testament to the spirit of exploration. The moon is tidally locked with Earth. One side, the near side, perpetually faces our planet. The other side, the far side, always faces away. This creates an interesting problem for lunar missions. Anything operating on the far side of the moon has no direct line of sight to Earth. Radio signals can't pass through 3,400 kilometers of solid rock, which means that to communicate with rovers, landers, or astronauts on the far side, you need relay satellites in lunar orbit. The Soviet Union's Luna 3 probe, launched in 1959, was the first spacecraft to capture images of the far side of the moon. These grainy photographs revealed a heavily cratered landscape, starkly different from the near side's dark maria or seas. The far side of the moon is also known as the dark side, not because it lacks sunlight, but because it remains hidden from Earth's view. The far side of the moon presents unique challenges and opportunities for exploration. Its isolation from Earth's radio interference makes it an ideal location for radio astronomy, allowing scientists to study the universe at wavelengths that are impossible to observe from Earth. The Chang'e 4 mission, which landed on the far side of the moon in 2019, carries a low-frequency radio spectrometer designed to study the early universe and the epoch of reionization. However, the far side's isolation also poses significant communication challenges. To address this, China launched the Queqiao relay satellite in 2018, which orbits the Earth-Moon L2 Lagrange point and provides a communication link between the Chang'e 4 lander and Earth. The Queqiao satellite is equipped with a 4.2-meter parabolic antenna, which transmits data at a rate of up to 50 kilobits per second. NASA and other space agencies are already planning to deploy communication satellites around the moon as part of the Artemis program. The Lunar Gateway Station will provide some relay capability, and dedicated communication satellites will fill in the gaps. But here's where it gets complicated. Even with perfect communication infrastructure, there's still a delay. Light takes about 1.3 seconds to travel from the moon to Earth. That means any signal sent from the lunar surface takes 1.3 seconds to reach Earth, and any response takes another 1.3 seconds to return. That's a 2.6-second round-trip delay at minimum. During the Apollo missions, this delay led to moments of tension. For example, when Apollo 11's Eagle lander was descending to the moon, mission control had to wait anxiously for each update, unable to intervene in real time. The Apollo 13 mission, famously dubbed a successful failure, highlighted the challenges of communication delays when an explosion in the service module put the astronauts' lives in jeopardy. Ground crews had to work frantically to develop a solution using only the materials available on the spacecraft. The Apollo 13 mission, often referred to as a successful failure, is a testament to human ingenuity and resilience in the face of adversity. On April 13, 1970, an explosion in the service module's oxygen tank crippled the spacecraft, forcing the crew to abort their planned lunar landing. The astronauts, James Lovell, Jack Swigert, and Fred Hayes, faced a harrowing journey back to Earth, relying on the lunar module as a lifeboat. Ground crews worked tirelessly to devise a solution, using only the materials available on the spacecraft. The crew's safe return to Earth on April 17th was a triumph of human ingenuity and a testament to the power of teamwork and perseverance. The Apollo 13 mission highlighted the challenges of communication delays and the importance of contingency planning in space exploration. For casual communication, that's fine. For teleoperated robots, it's a problem. You can't drive a rover in real time with a multi-second lag. By the time you see an obstacle and tell the rover to stop, it's already driven into it. NASA's Mars rovers, such as Curiosity and Perseverance, operate with a similar delay, but their autonomous navigation systems allow them to detect and avoid obstacles without real-time human input. However, these rovers move at a glacial pace, covering only a few dozen meters per day. On the Moon, where gravity is 1/6 that of Earth, rovers could theoretically move much faster, but this would require even more sophisticated autonomy to avoid accidents. The Soviet Lunokhod rovers, which operated on the lunar surface in the 1970s, were remotely controlled by operators on Earth, but their slow movement and the communication delay limited their effectiveness. The Soviet Lunokhod program was a pioneering effort in lunar exploration, demonstrating the feasibility of remote-controlled rovers on the Moon. The Lunokhod 1 rover, launched in 1970, was the first roving remote-controlled robot to land on another celestial body. Equipped with a suite of scientific instruments, including a television camera and a soil mechanics tester, the rover explored the lunar surface for nearly 11 months, traveling a total distance of 10.5 kilometers. The Lunokhod 2 rover, launched in 1973, operated for about 4 months and covered 37 kilometers, setting a record for the longest distance traveled by a lunar rover. The Lunokhod rovers were controlled by operators on Earth who used a series of television images to navigate the lunar terrain. Despite their success, the rovers' slow movement and the communication delay limited their effectiveness. This means lunar systems need to operate autonomously, not just following pre-programmed instructions, but making decisions on their own. Navigation, obstacle avoidance, task prioritization, error recovery, all of it has to happen without human intervention. Autonomous systems exist. Mars rovers like Curiosity and Perseverance operate with similar constraints due to the much longer communication delay with Mars. But autonomy is hard. It requires sophisticated software, extensive testing, and even then things go wrong. A rover gets stuck, a sensor malfunctions, an unexpected situation arises that the programming didn't account for. In 2009, NASA's Spirit rover became trapped in soft Martian soil, leading to a months-long effort to free it. Ultimately, the rover remained stuck, and its mission ended in 2010. The Opportunity rover, Spirit's twin, operated for nearly 15 years, far exceeding its original 90-day mission, but its longevity was due in large part to the ingenuity of its Earth-based operators, who devised creative solutions to keep it going. The Spirit and Opportunity rovers, part of NASA's Mars Exploration Rover mission, were a testament to human ingenuity and perseverance. Launched in 2003, the rovers were designed to operate for 90 sols, Martian days, but far exceeded their expected lifespans. Spirit, which became trapped in soft soil in 2009, continued to operate as a stationary science platform until 2010. Opportunity, which landed on the opposite side of Mars, roamed the planet for nearly 15 years, traveling a total distance of 45 kilometers and making significant scientific discoveries. The rover's autonomous navigation systems allowed them to detect and avoid obstacles, but their success was also due to the ingenuity of their Earth-based operators, who devised creative solutions to keep them going. The rover's legacy continues with the Mars 2020 Perseverance rover, which landed on the Red Planet in February 2021. On Mars, when something goes wrong, engineers on Earth spend days or weeks figuring out a solution and uploading new commands. On the Moon, the expectation is that systems will be more responsive, more capable, more resilient, because the Moon is close enough that we should be able to fix problems quickly. Except we can't. Not if the problem is on the far side, not if it happens during the lunar night when power is limited and communication windows are narrow, not if it involves something that requires a human to physically intervene. During the Apollo 13 mission in 1970, an explosion in the service module put the astronauts' lives in jeopardy. Ground crews had to work frantically to develop a solution using only the materials available on the spacecraft. This improvisational approach is unlikely to work on the Moon, where the environment is far more unforgiving. The Apollo 13 mission highlighted the challenges of operating in a hostile environment with limited resources. The astronauts, faced with a life-threatening situation, had to rely on their training, ingenuity, and the support of ground crews to devise a solution. The mission's success was a testament to human resilience and the power of teamwork. However, the Moon's harsh environment poses even greater challenges. The lunar surface is exposed to extreme temperature swings, micrometeorite impacts, and intense radiation. Any human presence on the Moon will need to contend with these challenges, requiring robust and reliable systems that can operate autonomously and withstand the rigors of the lunar environment. For crewed missions, the autonomy requirement extends beyond robots. Life support systems, power generation, thermal management, radiation monitoring, all of it needs to function reliably with minimal oversight. Astronauts can't be constantly troubleshooting equipment failures. They have work to do, experiments to conduct, construction projects to complete. The International Space Station, ISS, for example, relies on a complex array of automated systems to maintain its environment, but astronauts still spend significant time performing maintenance tasks. On the Moon, where the environment is far more hostile, these systems would need to be even more robust and reliable. The ISS is a testament to human ingenuity and cooperation, but it operates in the relatively protected environment of low Earth orbit, far removed from the harsh realities of the lunar surface. The International Space Station, ISS, is a remarkable achievement of human engineering and cooperation. Orbiting at an altitude of about 400 kilometers, the ISS provides a unique microgravity environment for scientific research and technology demonstrations. The station's life support systems, which include the Environmental Control and Life Support System, ECLSS, maintain a habitable environment for the crew, recycling air and water and managing waste. The ISS is powered by a set of solar arrays, which generate up to 120 kilowatts of electricity, supplemented by batteries during periods of eclipse. The station's thermal control system, which includes radiators and heat exchangers, maintains a comfortable temperature for the crew. Despite its advanced systems, the ISS requires constant maintenance and upgrades, highlighting the challenges of sustaining a human presence in space. The more complex the systems, the more things that can go wrong, and the more autonomous those systems are, the less control humans have when something does go wrong. The Apollo 13 incident highlighted the dangers of relying on complex systems. When a single component failed, it triggered a cascade of problems that nearly ended in disaster. On the Moon, where the environment is even more unforgiving, such failures could be catastrophic. The Apollo program was a triumph of human ingenuity, but it was also a reminder of the fragility of our technology and the importance of redundancy and contingency planning. The Apollo 13 incident underscored the importance of redundancy and contingency planning in space exploration. The mission's success, despite the failure of a critical component, was a testament to the power of human ingenuity and resilience. However, the Moon's harsh environment poses even greater challenges. The lunar surface is exposed to extreme temperature swings, micrometeorite impacts, and intense radiation. Any human presence on the Moon will need to contend with these challenges, requiring robust and reliable systems that can operate autonomously and withstand the rigors of the lunar environment. The Apollo program laid the groundwork for future exploration, but it also highlighted the need for continued innovation and adaptation. There's a loneliness to this that's worth acknowledging. For the first time in human spaceflight, astronauts on the far side of the Moon will be truly out of reach. When Apollo astronauts orbited the Moon, passing behind it meant a temporary loss of communication, 30 or 40 minutes of silence before they re-emerged on the near side. It was unsettling but brief. On the far side of the Moon, Earth isn't hanging in your sky. For the first time, we won't just be far from home. We will be out of reach. The Soviet Luna 2 probe, launched in 1959, became the first human-made object to reach the Moon. It impacted the surface on the far side, in the Palus Putridinus region, and was unable to transmit data back to Earth. This early mission foreshadowed the isolation that future lunar explorers would experience. The far side of the Moon is not just a geographical challenge, it is an existential one, a test of our ability to endure isolation and adversity in the pursuit of knowledge. The far side of the Moon presents unique challenges and opportunities for exploration. Its isolation from Earth's radio interference makes it an ideal location for radio astronomy, allowing scientists to study the universe at wavelengths that are impossible to observe from Earth. The Chang'e 4 mission, which landed on the far side of the Moon in 2019, carries a low-frequency radio spectrometer designed to study the early universe and the epoch of reionization. However, the far side's isolation also poses significant communication challenges. To address this, China launched the Kueqiao relay satellite in 2018, which orbits the Earth-Moon L2 Lagrange point and provides a communication link between the Chang'e 4 lander and Earth. The Kueqiao satellite is equipped with a 4.2-meter parabolic antenna, which transmits data at a rate of up to 50 kilobits per second. We like to imagine that every problem has a solution, that sufficient ingenuity, enough time, adequate resources, these things can overcome any obstacle. It's a comforting belief, and often it's even true. But the Moon doesn't care about our ingenuity. Lunar dust has been grinding down rocks for 4 billion years. It will continue grinding them down long after we're gone. The solar wind has been bombarding the surface with radiation since the Moon formed. Temperature swings have been cracking and reshaping the regolith through countless cycles of heating and cooling. The Moon's surface is pockmarked with impact craters, some dating back billions of years. These craters are silent witnesses to the Moon's violent history, a constant reminder of the forces that have shaped it over eons. The lunar surface is a geological time capsule, preserving the record of the early solar system in a way that no other celestial body can match. The Moon's surface is a testament to the forces that have shaped it over billions of years. The lunar regolith, a fine powder created by the relentless bombardment of micrometeorites, covers the Moon's surface to a depth of several meters. This regolith is composed of fine particles of silicon, iron, calcium, and magnesium, as well as trace amounts of other elements. The lack of an atmosphere on the Moon means that these particles are exposed to the vacuum of space, resulting in a unique chemical composition that differs from that of Earth's soil. The lunar regolith is also electrically charged due to the bombardment of solar wind particles, which can cause it to cling to surfaces and create static discharges. The Apollo astronauts reported that lunar dust clung to their spacesuits, obscured their visors, and even found its way into the lunar module, where it contaminated equipment and irritated their eyes and throats. None of these are problems for the Moon. They're only problems for us. NASA, ESA, private companies, they're all working on solutions. Electrodynamic dust shields that repel particles using electric fields, magnetic filters that pull nanophase iron from the air, thermal coatings inspired by the lotus leaf effect, reducing dust adhesion, autonomous systems with sophisticated AI, nuclear reactors the size of garbage cans, habitats buried under meters of regolith. The Lunar Gateway, a planned space station in lunar orbit, will serve as a staging point for future missions, providing a safe haven for astronauts and a platform for scientific research. However, its construction and operation will face the same challenges posed by the lunar environment. The Gateway is envisioned as a critical component of the Artemis program, enabling sustainable lunar exploration and paving the way for future missions to Mars. Electrodynamic dust shields are one of several technologies being developed to address the challenges posed by lunar dust. These shields use electric fields to repel charged particles, preventing them from settling on surfaces. Researchers at NASA's Glenn Research Center are experimenting with various designs, including a concept that uses a series of concentric rings to generate an electric field. Magnetic filters, another promising technology, use powerful magnets to attract and capture iron-rich particles, which can then be removed from the environment. Thermal coatings inspired by the lotus leaf effect, which causes water to bead up and roll off the leaf's surface, are being developed to reduce dust adhesion. These coatings, which mimic the nanoscale structures found on the lotus leaf, create a surface that is both hydrophobic and oleophobic, repelling both water and oil. Some of these will work. Many already do to an extent. But every solution reveals new complications. Electrostatic shields require power, which means more solar panels, which means more surface area for dust to accumulate on. Magnetic filters capture iron-rich particles, but they do nothing about the rest of the dust, and they need regular cleaning, which exposes workers to more dust. The lunar regolith is not just dust, it's a complex mixture of minerals, including silicates, iron, calcium, and magnesium. These particles are sharp, abrasive, and can cause mechanical and electrical failures in equipment. The Apollo astronauts reported that lunar dust clung to their spacesuits, obscured their visors, and even found its way into the lunar module, where it contaminated equipment and irritated their eyes and throats. The Apollo astronauts' experiences with lunar dust highlighted the challenges of operating in the moon's harsh environment. The dust, which is electrically charged due to the bombardment of solar wind particles, clung to surfaces and created static discharges. The astronauts reported that the dust obscured their visors, making it difficult to see, and found its way into the lunar module, where it contaminated equipment and irritated their eyes and throats. The Apollo 17 mission, the final voyage of the Apollo program, brought back nearly 110 kilograms of lunar rocks and soil, providing scientists with invaluable insights into the moon's history and composition. However, these samples also highlighted the challenges of dealing with lunar dust, which clung to equipment and contaminated experiments. Autonomous systems can make decisions, but they can't improvise the way humans can, and they certainly can't fix themselves when something breaks. The Mars rover Opportunity, which operated for nearly 15 years, faced numerous technical challenges, including dust storms that blocked sunlight and limited its power. Engineers on Earth had to devise creative solutions, such as positioning the rover to maximize solar exposure to keep it operational. On the Moon, where conditions are even harsher, such improvisation would be even more critical. The lunar environment is unforgiving, and the ability to adapt and innovate in real time will be essential for the success of future missions. The Soviet Lunokhod rovers, which operated on the lunar surface in the 1970s, were remotely controlled by operators on Earth, but their slow movement and the communication delay limited their effectiveness. The Mars rover Opportunity, part of NASA's Mars Exploration Rover mission, was a testament to human ingenuity and perseverance. Launched in 2003, the rover was designed to operate for 90 sols, Martian days, but far exceeded its expected lifespan, roaming the red planet for nearly 15 years. Opportunity made significant scientific discoveries, including the detection of hematite spherules, known as blueberries, which provided evidence of past water activity on Mars. The rover's autonomous navigation systems allowed it to detect and avoid obstacles, but its success was also due to the ingenuity of its Earth-based operators who devised creative solutions to keep it going. The rover's mission ended in 2018, when a global dust storm blocked sunlight and limited its power, highlighting the challenges of operating in a harsh environment. The truth is that we're not solving these problems so much as managing them, finding ways to reduce exposure, mitigate risks, buy ourselves a little more time before something critical fails. That might be enough for short missions, weeks or months at a time. But for permanent habitation, for the vision of lunar bases and off-world industry and humanity spreading beyond Earth, the moon isn't cruel. It simply doesn't care. The Apollo missions brought back nearly 842 pounds, 382 kilograms, of lunar rocks and soil, providing scientists with invaluable insights into the moon's history and composition. However, these samples also highlighted the challenges of dealing with lunar dust, which clung to equipment and contaminated experiments. The lunar regolith is not just an inconvenience. It is a fundamental part of the moon's environment, and any human presence will have to contend with its unique challenges. The Apollo missions brought back a wealth of scientific data, including nearly 842 pounds of lunar rocks and soil. These samples, which were collected from various locations on the moon, provided scientists with invaluable insights into the moon's history and composition. The lunar rocks, which are primarily composed of silicates, iron, calcium, and magnesium, are believed to be among the oldest in the solar system, dating back billions of years. The Apollo missions also highlighted the challenges of dealing with lunar dust, which clung to equipment and contaminated experiments. The lunar regolith is not just an inconvenience. It is a fundamental part of the moon's environment, and any human presence will have to contend with its unique challenges. The Apollo 17 mission, the final voyage of the Apollo program, brought back nearly 110 kilograms of lunar rocks and soil, providing scientists with invaluable insights into the moon's history and composition. There's a certain humility in that realization. We've been to the moon before, but we were visitors. Brief ones. Now, we're trying to move in, to establish ourselves as residents, and the moon is reminding us that this isn't our environment. We're adapted for Earth, for breathable air and magnetic shielding and liquid water and daylight cycles that last hours instead of weeks. Every system we bring to the moon is a piece of Earth we're trying to preserve in a place that has no interest in preserving it. The lunar surface is littered with the remnants of past missions, from discarded equipment to crashed spacecraft. These artifacts serve as silent reminders of the challenges and risks of lunar exploration. The Apollo 11 landing site, Tranquility Base, remains a poignant symbol of human achievement, but it is also a testament to the harsh realities of the lunar environment. The Apollo 11 landing site, Tranquility Base, is a poignant symbol of human achievement and a testament to the harsh realities of the lunar environment. The site, which was designated a UNESCO World Heritage Site in 2019, is marked by the remains of the lunar module's descent stage, the American flag planted by the astronauts, and various pieces of equipment left behind. The lunar surface is also littered with the remnants of other missions, including the Soviet Luna 2 probe, which impacted the far side of the moon in 1959, and the Chinese Chang'e 4 lander, which has been operating on the far side since 2019. These artifacts serve as silent reminders of the challenges and risks of lunar exploration, as well as the ingenuity and perseverance of the humans who dared to venture beyond Earth. Maybe that's the real fatal flaw. Not the dust or the radiation or the cold or the darkness, but our assumption that these are problems with solutions, that given enough time and money and effort, we can engineer our way into making the moon habitable. Perhaps some flaws aren't meant to be solved. Perhaps some environments are hostile, not because they're broken, but because they were never designed for life in the first place. And perhaps the question isn't whether we can overcome the moon's hostility, but whether we should. The lunar surface is not just a barren wasteland, it's a geological treasure trove, preserving the history of the early solar system. Any human presence risked contaminating this scientific record, raising ethical questions about our right to disturb it. The Apollo missions were a triumph of human ingenuity, but they were also a product of their time, driven by the political and technological imperatives of the Cold War. Today's lunar ambitions are motivated by different goals, including scientific discovery, resource utilization, and the establishment of a permanent human presence beyond Earth. The Artemis program, named after the twin sister of Apollo in Greek mythology, aims to land the first woman and the next man on the moon by 2025. This mission represents a new chapter in lunar exploration, one that seeks to establish a sustainable human presence on the moon. The Artemis program, named after the twin sister of Apollo in Greek mythology, represents a new chapter in lunar exploration. The program aims to land the first woman and the next man on the moon by 2025, paving the way for future missions to Mars. The Artemis missions will face challenges that their Apollo predecessors could hardly have imagined, but they will also have the benefit of decades of technological advancement and the collective knowledge of the global space community. The program's goals include the establishment of a sustainable human presence on the moon, the development of new technologies for lunar exploration, and the advancement of scientific research. The Artemis program is a testament to human ingenuity and perseverance, as well as the enduring spirit of exploration that drives us to push the boundaries of what is possible. Every footprint we leave on the lunar surface stirs a cloud of dust that takes hours to settle in the weak gravity. It clings to our boots, our suits, our equipment. It gets tracked into habitats where it floats in the air. Too small to see, but large enough to irritate lungs and damage machinery. We brush it off, filter it out, seal it away, but it always finds a way back in. The Apollo astronauts described the lunar dust as having a distinctive smell, like gunpowder or burned charcoal. This scent is the result of the regolith's unique chemistry, shaped by billions of years of exposure to the solar wind and micrometeorite impacts. The lunar dust is not just a nuisance, it is a tangible link to the moon's ancient past, a reminder of the forces that have shaped it over eons. The Apollo astronauts' descriptions of the lunar dust highlighted its unique properties and the challenges it posed. The dust, which is electrically charged due to the bombardment of solar wind particles, clung to surfaces and created static discharges. The astronauts reported that the dust obscured their visors, making it difficult to see, and found its way into the lunar module, where it contaminated equipment and irritated their eyes and throats. The dust also had a distinctive smell, like gunpowder or burned charcoal, which was the result of its unique chemistry. The lunar regolith is not just dust, it is a complex mixture of minerals, including silicates, iron, calcium, and magnesium. These particles are sharp, abrasive, and can cause mechanical and electrical failures in equipment. The Apollo astronauts reported that lunar dust clung to their spacesuits, obscured their visors, and even found its way into the lunar module, where it contaminated equipment and irritated their eyes and throats. Dust on the moon doesn't settle the way it does on Earth. It lingers, it accumulates, it reminds us with every step that this place is not ours. The lunar regolith is not just an inconvenience, it's a fundamental part of the moon's ecosystem. Disturbing it could have unforeseen consequences, both for the lunar environment and for any human inhabitants. The Apollo astronauts reported that lunar dust was a constant challenge, clinging to their spacesuits and equipment, obscuring their vision, and even finding its way into the lunar module. Despite these challenges, the astronauts were able to collect valuable scientific data and bring back samples that continue to inform our understanding of the moon's history and composition. The lunar regolith is a geological treasure trove, preserving the record of the early solar system in a way that no other celestial body can match. Any human presence on the moon will have to contend with the unique challenges posed by lunar dust, as well as the ethical questions surrounding the disturbance of this scientific record. The lunar regolith is a geological treasure trove, preserving the record of the early solar system in a way that no other celestial body can match. The moon's surface is pockmarked with impact craters, some dating back billions of years. These craters are silent witnesses to the moon's violent history, a constant reminder of the forces that have shaped it over eons. The lunar surface is also littered with the remnants of past missions, from discarded equipment to crashed spacecraft. These artifacts serve as silent reminders of the challenges and risks of lunar exploration, as well as the ingenuity and perseverance of the humans who dared to venture beyond Earth. The Apollo 11 landing site, Tranquility Base, remains a poignant symbol of human achievement, but it is also a testament to the harsh realities of the lunar environment. The lunar regolith is not just dust, it is a complex mixture of minerals, including silicates, iron, calcium, and magnesium. These particles are sharp, abrasive, and can cause mechanical and electrical failures in equipment. The Apollo astronauts reported that lunar dust clung to their spacesuits, obscured their visors, and even found its way into the lunar module, where it contaminated equipment and irritated their eyes and throats. Maybe one day we'll find better ways to cope with it. Better filters, better materials, better understanding of how to coexist with lunar regolith. Maybe advances in nanotechnology or material science will give us tools we can't even imagine yet. Maybe the children of the first lunar colonists will adapt in ways we can't predict, developing technologies and techniques that make living on the moon as routine as living in Antarctica is today. The International Space Station has been continuously inhabited since 2000, demonstrating humanity's ability to adapt to extreme environments. However, the ISS operates in the relatively protected environment of low Earth orbit, shielded from the harsh conditions of the lunar surface. The challenges of living on the moon are far greater, but they are not insurmountable. With ingenuity, perseverance, and a deep respect for the lunar environment, humanity may one day establish a permanent presence on the moon. The Artemis program represents a new chapter in this quest, one that seeks to build on the legacy of Apollo and establish a sustainable human presence on the moon. The International Space Station, ISS, is a testament to human ingenuity and cooperation. Orbiting at an altitude of about 400 kilometers, the ISS provides a unique microgravity environment for scientific research and technology demonstrations. The station's life support systems, which include the Environmental Control and Life Support System, ECLSS, maintain a habitable environment for the crew, recycling air and water, and managing waste. The ISS is powered by a set of solar arrays, which generate up to 120 kilowatts of electricity, supplemented by batteries during periods of eclipse. The station's thermal control system, which includes radiators and heat exchangers, maintains a comfortable temperature for the crew. Despite its advanced systems, the ISS requires constant maintenance and upgrades, highlighting the challenges of sustaining a human presence in space. The ISS has been continuously inhabited since 2000, demonstrating humanity's ability to adapt to extreme environments. However, the challenges of living on the moon are far greater, but they are not insurmountable. With ingenuity, perseverance, and a deep respect for the lunar environment, humanity may one day establish a permanent presence on the moon. Or maybe decades from now, we'll look back at our lunar ambitions the way we look back at so many grand projects, necessary stepping stones, important learning experiences, but ultimately temporary. Maybe the moon will remain what it's always been, a place we visit, study, and admire from afar. The Apollo program was a triumph of human ingenuity, but it was also a product of its time, driven by the political and technological imperatives of the Cold War. Today's lunar ambitions are motivated by different goals, including scientific discovery, resource utilization, and the establishment of a permanent human presence beyond Earth. The Artemis program represents a new chapter in lunar exploration, one that seeks to build on the legacy of Apollo and establish a sustainable human presence on the moon. The Artemis astronauts will face challenges that their Apollo predecessors could hardly have imagined, but they will also have the benefit of decades of technological advancement and the collective knowledge of the global space community. The Artemis program, named after the twin sister of Apollo in Greek mythology, aims to land the first woman and the next man on the moon by 2025. This mission represents a new chapter in lunar exploration, one that seeks to establish a sustainable human presence on the Moon. The Artemis program, named after the twin sister of Apollo in Greek mythology, represents a new chapter in lunar exploration. The program aims to land the first woman and the next man on the Moon by 2025, paving the way for future missions to Mars. The Artemis missions will face challenges that their Apollo predecessors could hardly have imagined, but they will also have the benefit of decades of technological advancement and the collective knowledge of the global space community. The program's goals include the establishment of a sustainable human presence on the Moon, the development of new technologies for lunar exploration, and the advancement of scientific research. The Artemis program is a testament to human ingenuity and perseverance, as well as the enduring spirit of exploration that drives us to push the boundaries of what is possible. The Artemis astronauts will face challenges that their Apollo predecessors could hardly have imagined, but they will also have the benefit of decades of technological advancement and the collective knowledge of the global space community. For now, we press forward. We build our landers and test our habitats and train our astronauts. We develop countermeasures and contingency plans and backup systems for our backup systems. We do this because we're explorers, because we're curious, because the unknown has always called to us, even when it promised nothing but hardship. The Artemis program, named after the twin sister of Apollo in Greek mythology, aims to land the first woman and the next man on the Moon by 2025. This mission represents a new chapter in lunar exploration, one that seeks to establish a sustainable human presence on the Moon. The Artemis astronauts will face challenges that their Apollo predecessors could hardly have imagined, but they will also have the benefit of decades of technological advancement and the collective knowledge of the global space community. The Artemis program is a testament to human ingenuity and perseverance, as well as the enduring spirit of exploration that drives us to push the boundaries of what is possible. The Artemis astronauts will face challenges that their Apollo predecessors could hardly have imagined, but they will also have the benefit of decades of technological advancement and the collective knowledge of the global space community. But let's be honest about what we're doing. We're not conquering the Moon. We're negotiating with it, asking it politely to let us stay for a while, hoping it doesn't notice us too much. Every now and then, when the dust settles just right, and the Earth hangs in the black sky, and the stars stretch out forever in every direction, we might catch a glimpse of what drew us here in the first place, the wonder of it. The sheer audacity of standing on another world. And then we'll go back inside, seal the airlock, and spend the next hour trying to get the dust out of our equipment, because that's what living on the Moon means, not triumph, not conquest, just endurance. One dust particle at a time. The Apollo astronauts described the lunar surface as a place of stark beauty, a desolate landscape that nevertheless inspired awe and wonder. They spoke of the silence, the stillness, and the overwhelming sense of isolation that came with being so far from home. The lunar surface is not just a barren wasteland, it's a geological treasure trove, preserving the history of the early solar system. Any human presence on the Moon will have to contend with the unique challenges posed by lunar dust, as well as the ethical questions surrounding the disturbance of this scientific record. In the end, the Moon may remain a place of wonder and mystery, a silent sentinel in the night sky. It has inspired poets, scientists, and dreamers for millennia, and it will continue to do so long after our footprints have faded from its surface. The Moon challenges us to push the boundaries of what is possible, to question our assumptions, and to confront the limits of our ingenuity. And in doing so, it reminds us of the fragility and resilience of our own planet, the only home we have ever known. The Moon is not just a destination, it is a mirror that reflects our aspirations, our fears, and our enduring curiosity. It is a symbol of humanity's unending quest to explore the unknown and to understand our place in the universe. The Artemis program represents a new chapter in this quest, one that seeks to build on the legacy of Apollo and establish a sustainable human presence on the Moon. In doing so, it will inspire future generations to reach for the stars and to dream of the day when humanity becomes a truly multiplanetary species. The lunar night is a silent, unyielding force, a reminder of the Moon's indifference to human ambition. Its darkness and cold are not merely obstacles to overcome, but fundamental aspects of the lunar environment that will shape every facet of future exploration. The long nights will test the ingenuity, resilience, and determination of those who dare to call the Moon home. Yet, despite these challenges, the allure of the Moon remains undiminished. It beckons us with promises of discovery, innovation, and the opportunity to push the boundaries of human achievement. The Artemis program, with its goal of establishing a sustainable human presence on the Moon, embodies this spirit of exploration and perseverance. As we continue to reach for the stars, the lessons learned from the lunar night will guide us, reminding us that the path to the cosmos is paved with both triumph and adversity. And so, we press on, driven by the timeless human impulse to explore, to understand, and to endure.